Maybe he'll feel
Yep.
bad.
Are you, what's this, does the 7 just, did you just put that for how, oh yeah, for how many like units there are? Okay.
Yep.
I was, okay.
I'm going over section 2 of chapter 1 at the moment.
Please, can we do that? I will wake up early just to get ready.
Me too.
Boys and girls, time to stop talking. Thank you. In chapter 1, we introduced and or reviewed the different units that are common in our class. They are listed up there. Please note that mass should be in kilograms, so if you're given a mass in grams or pounds or whatever it might be, it needs to be converted. The 2 types of unit conversions were also discussed, so using prefixes to go from, say, meters to kilometers or milliliters to liters and things like that, and or moving from English to metric conversions. Those are ones you'd have to be given the conversion factor in order to convert. So if you're trying to convert hours to minutes, you need the fact that there are 60 minutes in an hour in order to do so. Some kind of a conversion factor would be necessary for that particular section. In section 3, we reviewed sig figs, accuracy, and precision. So results specifically in any science are only as accurate as the measurement tools. Think how well you can actually read the ruler. Can you estimate the last digit? Yes.
Is that pound to gram?
Yeah.
Okay.
Like example of English to metric or something along those lines. Some kind of a conversion that requires a conversion factor.
Okay.
Could be hours to seconds. Again, requires a conversion factor. So 2 types of conversions that you're expected to understand. When we say that results are only as accurate as the measurement tools, we can think like the last digit of any measurement is always estimated. So that last digit is where we introduce uncertainty. And that was something that was discussed in this section as well. How to calculate a percent uncertainty, what uncertainty means, and so on. From there, sig figs. In section 3, rules for sig figs. I will not go over them in depth today just because I have a lot of other things I would rather go over, like the kinematics formulas in section 2. So for sig figs, please make sure you go through and you remember how to interpret them. So a number like this, leading zeros never count. Leading zeros don't count. Sandwiched zeros always do. And last digits always count. Last zeros or trailing zeros always count if there is a decimal present. Yeah, it is. Only if a decimal. Doesn't matter where the zero is located if it's a trailing zero, as long as a decimal is present, right? So this number has 1 sig fig. This number has 4 sig figs. because the decimal is present. Okay, so this particular number has 5 sig figs. Because the trailing 0 counts, since it does come after a decimal.
Oh, so that's what the decimals like right after it.
Doesn't matter where the decimal is located in the number, as long as there's a decimal, that means the trailing 0 will count. Okay, very last thing in chapter 1 was approximation. This is where you had to go through and you had to make reasonable approximations. The average heart beats 72 times a minute. Then you can multiply the number of minutes in a day up to how the length of the average human lifespan. As long as you can reason out why you're making the approximations or the assumptions you're making, that's what we call a reasonable approximation. Okay. From there, we move on to section or chapter 2. And chapter 2 is long. We introduced in chapter 2 movement. Can I erase this stuff?
What does it say on the far right?
Trailing zeros count only if a decimal is present. First topic in section 2, or chapter 2, was displacement. Which was distance from a starting point. Not to be confused with distance, which we discussed as total traveled. So in other words, if you're at home, if you're here and you travel to school, and then you travel to the store, and then you travel home again, your displacement is 0. But your distance is whatever this plus this plus this is. Okay, so remember that there was a difference between the two. This guy is a vector. This guy is a scalar. Remember that vector quantities have direction and magnitude. So if we wanted to talk about displacement, we would want to say something along the lines of 75 kilometers to the west. We have to give both a direction and a magnitude. Scalar quantities are just going to be numbers that have magnitude. So 35 miles does not tell you where from the starting point, just tells you how far. So that was 2.1. 2.2 was on vectors, scalars, and the coordinate system. In other words, chapter 2.2 told us that everything in the first quadrant was going to have a positive value. Everything in the third quadrant was going to have a negative value, and then you have positive y, negative y. Okay, so the coordinate system just set up our overall problems. The other thing that the coordinate system did was establish that starting positions at a 0 point, right? So whenever we start our problems in kinematics, we typically start at a 0 point. We said x was 0, we said y was 0, and then things changed from that initial point. Okay? Section 3 introduced. Can I erase this stuff? Okay. Section 3 introduced speed, velocity, and time. Time is always going to be given in seconds, and it's always positive. Right? Time is negative, never negative. We also said that delta t would just be replaced by t, because t initial is always 0. Right? Whenever we start timing something, we always start at 0. And so since it's always 0, we can abbreviate the change in time as velocity, or let's start with speed. Speed is defined as total distance over total time. And this has units of meters per second, just like everything else that we would talk about with velocity. But no direction. So it's never negative. Doesn't matter what direction of speed. We say the car goes 35 miles per hour. We don't give any information about direction or change in speed. Velocity, then, is speed plus a direction, also known as delta x over t, or displacement over time. Again, units are always going to be meters per second with direction. And here's where we talk a little bit about the types of directions that we can use in physics. Direction can be as simple as positive, negative. As we said in our coordinate system, if we're going to the right, direction is positive. Okay? Direction can be north, south, east, west. Direction can be up, down. Direction can be an angle. And direction can be left, right. Just some examples. So this is v at any time point. We also said that we could do an average v of 2 time points. We introduced our first kinematics equation in this section. I didn't call it that. That was section 3. In section 4, we introduced acceleration. image acceleration. Change in velocity over time. Remember that when you see VF, it means final. When you see V naught, it means initial. Later on, when we get to our formulas, solving any equation using kinematics equations, we get rid of the F altogether and just say that if you see a V, it means final. If you see V naught, it means initial though, and keep the little knots, okay? SI unit, meters per second squared. Okay, from there we had to have conversations about the sign of acceleration. Remember that this is also a vector. If V is positive and A is negative, it means it goes the opposite direction of velocity. So, in this situation, what is happening?
Slowing down.
The object is slowing down. Okay? If V is positive, and A is positive, what is happening to the object? Object is speeding up. Okay? So remember that acceleration is going to be determined to having an effect on motion, but you have to look at the signs of the motions first. So if we have V negative and A negative, what's happening?
Moving left.
The object is speeding up to the left, right? And then our last one was V negative with A positive. What's happening here?
Speeding up to the right.
You think so? Is our object speeding up or slowing down? When they're opposite, they're slowing down. To the right. Oops, to the left, sir. Right? Because velocity tells you direction of motion. Acceleration tells you if the object is speeding up or slowing down. Okay. Next is kinematics formulas in one dimension. The formula sheet for your final exam has been posted on Canvas for you to see. So please make sure you look at that this weekend to identify which formulas you'll need, / which ones you'll be given. Motion equations in one dimension. For this particular one, it was the x dimension. So if we're talking about one-dimensional motion, which means usually the x direction, a couple of things that we are going to assume. Remember we said delta t is t. We said delta x would be these are all of our assumptions. Using these assumptions, we get these equations. You get these guys? Section 6 introduced how to solve problems using these equations. Yeah,
Does that say for equation 4, 1 over what?
1/2, yeah. Sorry. First step was to draw a picture. Second step was to make a list. Step 3. Oops. Unknowns. Step 4. Find an equation. Step 5, anybody remember?
Checking.
Plug and chug. Gotta do the math first. And then step 6, is it reasonable? Yeah. I will remind you that for steps 2 and 3, we introduced the table of variables. You don't have that. So, oh my gosh. X. Oops, not AX, sorry. Table of variables. For one-dimensional motion, we're either dealing with x's or y's, not both. So we only make a list of the variables that we know. We would identify all the ones we know. So steps 2 and 3 are to fill it in, right? Step 4 is to look at our equations, which one makes the most sense to help us solve what we need. Plug and chug, check your answers. Kind of vaguely ringing bells, hopefully, right?
Yeah.
Okay. Do we have these guys written down? Because I'm going to erase and do the y formulas next. Because the next section, 7, was on the y direction. So free fall, right? Yep.
For these problems, is it still either V and or V naught are the same usually? Or is that later?
No, those are completely different. Those are two-dimensional motion, projectile motion assumptions. Yes. If you haven't already found the formula sheet for next week's final exam, I highly recommend you get that open and have it in front of you right now. Put it on your phone, put it on your computer, I don't care, but I want you to see how they're laid out on that formula sheet so that you understand what you need to make sure you know about that formula sheet, okay? All right, so this was free fall. So in other words, one-dimensional motion in the y direction. The problem-solving steps are going to be the same. What's different are the equations. Oh boy, I'm gonna do this from heart. Okay. I'm only gonna do equations 3, 4, and 5 because equations 1 and 2, you just change the y's. But equation 3 becomes that one. Equation 4 becomes this. That. The table then has an assumed value of g. Now what happens if instead of being on Earth we're on the moon? What happens to that gravity value?
Goes away.
It changes, right? It becomes a different value. But it still could have the fall in motion. We would just need to know what that gravitational value was for a different plane, different area, different body. Okay? Okay. The last thing in chapter 2 was graphs. Going from position versus time to velocity versus time and acceleration versus time. And interpreting them in whichever way necessary. Yep.
The sheet for the equations online is blank. Are we filling it out for the fun?
Say again?
It's blank.
What do you mean?
It doesn't work on the computer.
No, there should be like an actual.
Yeah, mine popped up. I think it's just
Okay.
because it's
It might be on your phone. That might be why.
never mind.
You're okay. I don't want you to think it's actually. Okay, well that's not helpful. I am only gonna finish going over chapter 2 today. After that, I'm gonna give you some time to start pulling some stuff out from chapter 2, your notebooks, looking over problems. You need to spend time with these problems, right?
Yes.
Plenty that you can be doing on OpenStax, and I'll show you where to find them. Okay. So here is the final exam equation sheet. You'll notice that you do not get y formulas. I am assuming, okay, that you can convert the x formulas into y's. That's the one thing I did not include. So you may want to try to commit these to memory or figure out the way to commit these to memory, because I don't think these are on there, are they? Oh wait, come on. They're there. But it's part of the two-dimensional. Remember, we'll talk about the assumptions for the x and y's. Okay, my bad. But just remember what they are. Now, they should be in the order that we've just written them too. So like equation 3, 4, and 5 should still be 3, 4, and 5 on here. You've also got some formulas from section 3 when we started doing vectors on angles and two-dimensional motion. Okay, so let's go over our last topic in section 2. In chapter 2. Why do I keep saying section? Okay, whatever. Chapter 2. Can I erase these then? We good? We understand? Same exact approach to problem solving in the y direction as we took in the x direction. Just different equations. All right. So 2.8 graphs. Woo! So let's start with, where do you want to start? You want to start with position, velocity, or acceleration?
Position.
You're going to start with position first? Okay. So let's do a position time graph that goes below the axes at the end.
Is that a plus sign?
That's an X.
Oh, sorry.
X is position, Okay. So we're going to start from the origin on our position. And we're going to change position time slowly but surely. But we're going to really try to hammer home like where it's constant, where it's changing, where it's positive, where it's negative, things like that. When we do these, we analyze our graph to look for slopes, because what we're going to graph on our next graph is a changing slope. Okay? So over here, positive or negative slope? Positive. And you'll remember we did like 3 positives. Pretty steep slope, right?
Yes,
Okay. Up here, still pretty positive, right?
but 2.
Okay. Okay? Up here,
1.
we still have a positive slope, but is it starting to like level off, maybe become 0 for like a fraction of a second at the top of its motion? Yes, it is. Okay, then what happens?
Negative.
My slope becomes negative. My slope becomes even more negative. And then it looks like it stays constant for the remainder of the motion. Guys, these are derivatives.
Yeah.
Anna's face just went, oh crap. I taught you how to do derivatives before you did derivatives in the mathematical sense. What? All right. Over here, velocity time. Positive, positive, positive means above or below the axes. Above, way above. Way above. For that first time frame. All right, then what happens? Are we still positive? Yes, but it's getting less, right? So we're going to go down.
Oh, I forgot these are the blocky ones.
Yep, these are the blocky ones. All right, what happens next? It's still positive, but it's getting less. Oh, I'm sorry. Actually, these aren't the blocky ones. Let's do dots. Remember, we do dots. It's okay. So very positive slope up here, becoming less positive as we go down. Becoming less positive as we go down. What happens next? It's negative, but it's a small negative, right? And then it's more negative, right? And then it's more negative. And then it kind of stays constant at the negatives, right? So down here, we can put dots like that. Then we connect the dots. It should be a straight line. Mine doesn't look straight, but it's supposed to be a straight line. Straight, constant, decline. Okay, now let's do the same thing we did here. Over here. Positive or negative slope? Negative. Positive or negative? Positive or negative?
A whole lot of negative.
Is it a constant negative slope? Yes. Constant
That means a straight line. It's linear.
negative means straight line over here, right? Unchanging acceleration, but a constant acceleration down here somewhere.
Linear.
Okay. Oh, no, I did it wrong. No. I did it right by your pen.
Okay?
That's a bit mean. That's lower.
All right, all right. Is this kind of ringing some bells? Do we
Yes.
remember a little bit? You're gonna want to practice this on your own. You can find position time graphs. You can find velocity time graphs.
This makes more sense than when I learned it.
Same.
Probably because you've now understood that what you're graphing is the area under a slope. All right, let's do another one.
I don't know.
So you're gonna want to redraw your acceleration, velocity, and position versus time. Empty ones.
I don't know what that is.
Okay, let's do another one. X, T. All right, this time I'm going to start with a velocity time graph. Okay, I'm going to do this. So which one do we want to do first? Do we want to do position time or do we want to do acceleration time? It's easier to go this way, right?
Yeah.
Okay, so let's do that. Let's take the slope at the points Looks like our slope starts positive but pretty shallow and becomes more and more and more positive, right?
Yep.
So if you graph each one of them, you should see a straight line with a constant slope. As we move up. Okay?
Won't acceleration like most of the time be constant?
Oh, cool. Thank you. Say again?
Oh, won't acceleration most of the time be constant?
Yes.
Okay.
Most of the time we deal with a constant, unchanging acceleration. But position time graphs are the one location where you can actually see a changing acceleration value. All right, so let's go backwards. Hi.
Hey, Mr. Gray.
Position time, velocity time, acceleration time graphs in physics. Yeah. Okay, so let's go backwards. What's up?
So why is it that even though it's a constant positive the acceleration?
Yes. So
why-
this would be like, whatever the slope of this is would give us information about the acceleration versus time.
So is that the reason why it's not like just straight across and above?
Yeah, so a lot of times we deal with like, okay, gravity is negative 9.8, right? And that means at any time point it's negative 9.8. But we can have changing accelerations. We don't deal with math in changing accelerations, ladies and gentlemen. We deal with math that has constant acceleration. So Olivia was asking, isn't it usually just like a straight positive or straight negative? Yes. Because in kinematics, we have to assume that acceleration is constant. Whether that means it's 0 or some other value, we have to assume it's constant for those formulas to work. Okay? All right, so let's go backwards. So in order to get from one to the next, okay, never mind, guys, that was the bell. We will continue on Monday.
Wait, yeah. That was a huge cliffhanger.
Okay, all right, so in order to get here, how did we get here first, is the question. We took the slope of these areas and we graphed them as points, didn't we?
Yes.
So this one, shallow positive, means it's going to be pretty close.
Is it like positive, just constant?
Okay, this one's is a less shallow positive, so this one's going to be up here. This one's going to be even more positive, so up here, then up here, up here. So what's going to happen is we're going to see a
Parabola.
steeper parabola than the one that we got over here.
That's kind of.
Crazy.
I thought it was gonna be a straight line. I would
Steeper parabola.